Yes, assalamu alaikum everyone. So today we are going to start with February-March 2023 paper 4-2. Okay. Let's start with question number 1. The most common zinc mineral contains zinc 2 sulfide. Complete the electrons in boxes diagram in 1.1. Show the electronic configuration of zinc 2 ions. So if you recall, zinc, its atomic number is 30. And when it becomes zinc 2 ions, it have a 2 positive charge. So here in its atom, it have a 30 electrons, but here the number of electrons are instead 28. Okay. So now I have to fill the electrons in these orbitals. So if I'll write the electronic configuration of zinc, you can easily figure it out. It's 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and 3d10. But when it becomes zinc 2 positive, then the 2 electrons from 4s would be removed and it becomes 4s0. So it means there must be no filling in the 4p. Now we are left with 3d and 4s. In 4s, there must be no filling. Okay, because these two are vacant. Now in 3d, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 10 electrons are filled. Now next part. Complete figure 1.2 to show the bond Haber diagram for the ionic solid zinc sulfide. Include state symbols of the relevant species. Okay. So if you see over here, they have mentioned the enthalpy change of formation and the reactants are missing. We got the product that is a 1 mole of an ionic compound. So if you recall enthalpy change of formation, it is formed from elements. It is the enthalpy change when 1 mole of a compound is formed from its elements. So here we would mention elements. Zinc is a metal, so it must be solid. Then we have sulfur, and sulfur is a non-metal, but it is also solid, yellow solid. So here we would mention elements. Now, if you see here on this arrow, they have mentioned atomization of zinc. So for the atomization of zinc, what would we write over here? Atomization, if you recall, it is the energy change when 1 mole of a gaseous atoms are formed from its elements. So as it's an atomization of zinc, so zinc turns into gaseous state and sulfur remains as a solid. Then first ionization energy. The ionization energy is for the one which turns into positively charged ions. So here zinc positive 1 and in a gaseous state, that is removed from the zinc and sulfur again stays solid.
Yeah.
Then sorry,
Yeah, atomization just
okay. Yes, 1 minute. Thank you, Taha. So in this case, here the atomization of sulfur is over here. Okay. So if you state the atomization of sulfur, so zinc 1 mole gaseous state and Here the sulfur was solid. Now here the sulfur becomes gas. Then now it's a first ionization energy. So the product of the first ionization energy must be mentioned over here. So zinc plus 1 ion in a gaseous state plus electron plus sulfur gaseous atom. And then the second ionization energy equation is also mentioned. Here equation is mentioned. Equation is mentioned over here, and all of the rest of them, right? So I think now nothing is missing. So we have to mention these four things. Okay. Let's next part. Describe the trend in the first electron affinity of the group 17 sulfur to tellurium. Okay. So in the periodic table, first element is oxygen in this group, then and after sulfur, I don't remember. Okay. You can find in the periodic table. We have selenium and tellurium. Okay. So after sulfur, we have a selenium and then we have a tellurium. Okay. So they have asked us about the electron affinities from sulfur to tellurium. So electron affinity is the energy change that is actually observed when one electron is being added in the outermost shell. So when we talk about sulfur, for example, if sulfur's atomic is this, then the atomic radius of selenium would be bigger than this, and then the atomic radius of the tellurium would be more bigger. So as the size gets bigger, the electron is actually that is going to be gained experiences the lesser forces of attraction from the nucleus because of its distance that it is getting away from the nucleus. So it means that it is going to be less exothermic down the group. So first what I will write that the first electron affinity gets less exothermic or instead of exothermic you can write negative from sulfur to selenium to tellurium. It is because the outermost shell gets further away from nucleus, hence the nuclear attraction decreases towards the incoming electron. Yes, is this clear to everyone?
Sir, can I state it in the way of more shielding from inner shells?
Yes, instead of writing, can you repeat what you just said?
I said like can I write it in the way like there's more shielding from the inner shells as we go down the group?
Yes, you can write instead of this that it is because the shielding increases. The shielding effect increases instead of this because of the more inner shells. Yeah, you can write that as well. Okay. Yes, is this clear, Ahmed?
Yes, sir.
Okay. Now the next part, explain why the lattice energy of zinc oxide is more exothermic than zinc sulfide. Okay. So if you look in the periodic table, see where is the oxygen and oxide ion and the sulfide ion. So obviously oxide ion is smaller and sulfide ion is a bigger ion. That due to its bigger size, the force of attraction between the zinc and the sulfide would be greater, would be smaller, would be lower because the charge density of the sulfide ion decreases. So here I can write that oxide ion is smaller in size than sulfide ion, hence stronger attraction between zinc ions and oxide ion. Instead that you can do the opposite argument, like instead of this you can uh, write in the aspect of a sulfide ion that sulfide ion is bigger than oxide, hence weaker attraction between zinc and sulfide. Is this clear?
Yes, sir.
Okay. Now, zinc metal can be obtained in a two-step process as shown. Okay, first zinc sulfide is turning into zinc oxide, then zinc oxide is actually reduced by carbon. The reactions are carried out at 800 degrees Celsius. Predict the sign of entropy change of the reaction in step 1. Yes, can anybody figure it out?
It will be negative.
Why?
Lesser molecules of gas and product.
Yes, very good. Because you can easily see that there are 2 moles of gases over here on the product side, and there are 3 moles of the gases in the on the reactant side. So the entropy decreases, so the change in entropy would be negative. Delta S is negative as the number of moles of gases on product side are less. Okay. Now, next part, use the data in table 1.1 to calculate entropy change of the reaction shown in step 2. Okay. In step 2, the reaction is, let me write the equation over here, that zinc oxide is reacting with carbon, forming molten zinc because the reaction is actually occurring at a higher temperature, and carbon monoxide gas. Okay. To find the entropy change, the entropy change of a reaction is equals to sum of the entropies of the reactants minus sum of the entropies of the product. So in the reactant, we have a zinc oxide and its entropy changes 43.7, plus we have a carbon, its entropy changes 5.7, minus in the product side, we have a 1 zinc molten, its entropy is 50.8, then carbon monoxide, and its entropy is 197.7. So can anybody solve and tell me the answer?
सर ये प्रोडक्ट्स माइनस रिएक्टेंट्स नहीं है?
One minute. Product minus reactant.
Sir, I think it's products minus reactants.
Yeah, it's product minus reactants. So just change the sign over here.
Sir, 199.1.
Sorry,
199.1.
199.1. The product minus reactant, and it's a positive, right?
Yes, sir.
So positive 199.1. Okay. Now next part. An equation for the direct reduction of zinc sulfide by carbon is shown. Okay. They have provided you the enthalpy change and the entropy change. The reaction is not feasible at 800 degrees Celsius. Calculate Gibbs change in Gibbs free energy for this reaction at 800 degrees Celsius. So the expression for the Gibbs free energy change is equals to delta H minus T delta S, T delta S. So see, it's in kilojoule. Gibbs free energy change is also in kilojoule, and it's in joule, so I have to divide it by 1000. So enthalpy change is positive 733 minus temperature. Remember that temperature must always be in Kelvin, and here they have given you the temperature at 800 degrees Celsius, so you have to add 273. So 800 plus 273 would be the temperature, then multiply by positive 218 over 1000. Yes, can anybody solve and tell me the answer?
Positive 499.1.
Positive 499.1. Okay. Now, C part, zinc nitrate undergoes thermal decomposition when heated. The reaction is similar to the thermal decomposition of group 2 nitrates. So if you recall, for the group 2 nitrates, when we decompose them, on decomposing, it turns into a metal oxide, nitrogen dioxide, and oxygen. So instead of M, we have to replace M by zinc. So zinc nitrate, you can either put a triangle or write heat above arrow. Zinc oxide would form along with, okay, 2 moles of nitrogen dioxide and half mole of oxygen. Okay. Now, next part, the radii of some group 2 cations and zinc are shown in the table 1.1. Okay. State and explain the trend in thermal stability of group 2 nitrates down the group. Okay. So we all know that down the group 2 nitrate, group 2, the thermal stability of nitrates decreases because the ion polarization gets lower due to the increase in the size of the cation. Okay. So the thermal stability increases. So sorry, the thermal stability increases. The thermal stability of the group 2 nitrates increases down the group due to increase in cationic size and as the cationic size increases, what would happen? The polarization of nitrate ion decreases, making nitrogen and oxygen bond more stronger. Use table 1.2 to suggest which group 2 nitrates are less thermally stable than zinc nitrate. Obviously, the one whose atomic radii or ionic radii would be actually smaller than zinc. So the atomic radii of zinc is 74 and magnesium have a smaller radii than zinc. So magnesium nitrate would be the one which is thermally less stable than zinc because its radius is smaller than zinc. So it decomposes more readily. So its thermal stability would be lower. Is this clear? Yes, if anyone have any doubt to ask. Yes, is this clear to everyone?
Yes, sir.
Okay. Now, question number 2. Hypophosphorus acid is an inorganic acid. The conjugate base of hypophosphorus acid is H2PO2 negative. Give the formula of hypophosphorus acid. So if it's a conjugate base of hypophosphorus acid, so it clearly means that it must be formed by the release of H positive. And it's a, so when we move back, so it would become H3PO2. So basically, this is the formula of hypophosphorus acid. So H3PO2. Is this clear? Okay, B part. This is the conjugate base, and it's a strong reducing agent, which means what would it do to itself? It would going to oxidize. It can be used to reduce metal cations without the need for electrolysis. Okay. So here we have equation 1, and they have provided us with the E naught values as well. In an experiment, the alkaline H3PO2 negative and H2PO2 negative half cell is constructed with H2PO2 negative ion concentration is 0.05 mole per dm³. The other ion are at the standard condition concentrations, which means the other ion have a concentration of 1 mole per dm³. Predict how the value of E of this half cell differ from its E naught value. So actually what they did, they have took its concentration lower than 1. So the equilibrium will going to shift towards right. And if equilibrium will shift towards right to reestablish itself, so what happens to the E naught value, whether it increases or decreases?
Increase.
Yes, it increases because the reduction occur more readily, and as a result, the E value, the E of this half cell would be greater than its E naught.
Sir, but isn't H2PO2 negative getting oxidized?
When it reacts with the other half cell, when it connected with the other half cell, then it would happen. But right now they are asking, see, they said that the other ion concentration is 1 mole per dm³, right? So if
Right.
this ion is 1 mole per dm³ and this ion is 0.05 mole per dm³ instead of being 1 mole per dm³, so what would happen? To reestablish the equilibrium would shift towards right. So as a result, that this HPO32 negative is going to reduce first to reestablish the equilibrium again, and as a result, the E value under non-standard conditions would increase because the reduction occur to restore the equilibrium. Okay.
Alright,
Sir,
sir.
आपको कैसे पता है कि ये इसकी concentration 1 है?
From this statement, that all the other ions are at the standard conditions. So standard condition says that when there is a standard condition, then the ion concentration is 1 mole per dm³.
Okay, sir. Thank you.
Okay, 1 mole per dm³. Standard conditions means 25 degrees Celsius. And if it's a pressure, so it must be 1 atm pressure. Okay, so we can state over here that as the concentration of H2PO2 negative is lower than standard concentration, the equilibrium shifts to the left. Sorry, the equilibrium shifts to the right. So the E, now I would write E instead of E naught because the conditions are non-standard. Okay, so the E of half cell would increases So you can write it this way, that E of a half cell is actually greater than the E naught, the potential, which is at 23.
तो मतलब सर जब भी इक्विलिब्रियम राइट की तरफ शिफ्ट होगा तो ई नॉट वैल्यू बढ़ जाएगी, ई वैल्यू बढ़
Oh,
जाएगी.
no, wait. There is an important thing over here to understand. In this case only, because in this case, the forward reaction is reduction. Okay. So if instead the equation is flipped, or the equation is in that way where the forward reaction is oxidation, in this case, the whole concept is reversed. When the forward reaction is oxidation, then if the equilibrium is shifting towards the right, then the E value decreases.
Okay, sir.
So you can remember this in that way, that if reduction would occur, E value increases, and if oxidation would occur, whether forward or backward, E value decreases. Is this clear to everyone?
Yes, sir.
Yes, sir.
Okay. Just give me a minute, please. Okay. Now here. The chromium 3 positive chromium half cell has a standard electrode potential of minus 0.74 volts. An electrochemical cell consists of an alkaline H3PO2 negative H2PO2 negative half cell and a chromium 3 positive chromium half cell. Calculate the E naught cell. So in this case, that would be very easy to do it, because if you see over here, its value is minus 1.57, right? And here its value is minus 0.74. So what was the expression to find the E naught cell? That E naught cell must be equals to E naught reduction minus E naught oxidation, right? So in the reduction one, we would use a greater value, a higher value. So here the reduction is taking place because this one is the greater value, and here the oxidation is taking place. So minus 0.74 minus 1.57. So can anybody solve and tell me the answer?
0.8.
Positive 0.83 volt, right?
Yes.
Okay. Now, complete the diagram in figure 2.1 to show how the standard electrode potential of the chromium 3 positive chromium half cell can be measured relative to that of standard hydrogen electrode. Identify the chemicals, conditions, and relevant pieces of apparatus. Okay. So here you can mention a hydrogen gas, and its pressure would be 1 atm and the temperature would be 24 degrees Celsius. Here you can put a voltmeter And then here we have our next electrode. Okay. So this is a hydrogen gas is being introduced. So this electrode must be platinum. And in the electrolyte, we have a hydrogen ions with 1 mole per dm cube concentration. Here, the electrode is of a chromium because we have a chromium and chromium 3 positive ion. So it must be a chromium. And in the electrolyte, we have a chromium 3 positive ions. And the concentration of chromium positive ions would be 1 mole per dm cube. And here it's a salt bridge. Okay. This diagram is clear to everyone.
Sir,
Yes, sir.
हर diagram के अंदर salt bridge बनाना होता है for every electrolysis.
Sorry.
हर diagram के अंदर salt bridge बनाना होता है.
Yes, whenever there is a half cell and when we are not using the electrolysis setup, but we are using the setup to produce the electricity, there is a salt bridge over there when there are 2 half cells. Okay.
Okay, sir.
Now, label figure 2.1 to show which is positive. So if you recall, where the oxidation is taking place is the one negative, and where the reduction is taking place is the one positive electrode. And direction of electron flow. So electron flow from always from the half cell where oxidation occurring towards the half cell where reduction is taking place. So the value for the chromium 3 positive chromium half cell is negative 0.74 volts. And for the standard hydrogen electrode is 0.00 volt. So this one is a bigger. So here reduction is occurring, here oxidation is occurring. If on hydrogen electrode reduction is occurring, then it would become a positive electrode and this one become a negative electrode. Okay. And the flow of electron is from here to here. Electron flow from the half cell where oxidation is taking place towards the half cell where the reduction is taking place. Is this understandable to everyone? Yes.
Yes, sir.
Yes, sir.
Okay. Now, fifth part. Okay. H2PO2 negative reduces nickel 2 positive to nickel in alkaline condition. Use equation 1 to construct the ionic equation for this reaction. Okay. Okay. So how would you make this? See, here they have told you that nickel reduces to nickel. So nickel 2 positive ion, sorry. Nickel 2 positive ion 1 minute, please. Let me write over here that they are saying that nickel to positive ions are turning into nickel, which means here the oxidation number is 0, which means 2 electrons are gained. Is this clear? Yes.
Yes, sir.
Okay.
Yes.
Now, from this first statement, what we can conclude that in this half cell reduction is taking place, right? So it means that in this equation 1, oxidation occur. So if the oxidation is taking place in this half cell, so if you see this equation, in this equation, there is a reduction in the forward reaction. So to make the ionic equation, you have to flip this equation. So I am writing this equation by flipping it over here. That here it becomes H2PO2 negative plus 3 hydroxide ions, giving you HPO3 negative plus 2 moles of water and plus 2 electrons. Now the electrons are equal in both the equations, but on opposite sides, so I cancel the electron. Then nickel to positive ions, H2PO2 negative plus 3 hydroxide ions, HPO3 negative plus 2H2O plus nickel. So this is the net equation for the reaction. There is a negative ion over here and there is, and this is the negative. Is this clear to everyone?
Sir, why haven't we flipped the nickel equation?
Why I haven't flipped the nickel equation? Because if you read this statement, what this statement is telling you, that nickel is being reduced, right?
Yes, sir.
So if you see this equation, which I have written over here, in this equation, the forward reaction is a reduction or oxidation.
Reduction.
So that's why I didn't flip. And if you look at this equation, in this equation, the forward reaction is a reduction or oxidation?
Reduction.
Reduction. But if this is undergoing reduction, then this clearly means then in this equation when the oxidation occur. And to show the oxidation, I have to flip this equation. Is it
Okay.
clear?
Yes, sir.
And then we have to look at the number of electrons on both the sides. If both the equations have the equal number of electrons, so just add the equations. Okay. Now, C part. What they are saying over here, that H2PO2 negative reacts with hydroxide ions. Okay. H2PO2 negative. Okay, here we have an equation. Table 2.1 shows the result of a series of experiments used to investigate the rate of this reaction. Okay. The volume of hydrogen was measured under room conditions. Okay. Use the molar volume of gas Vm and the data from experiment 1 to calculate the rate of reaction in mole per dm cube. Okay. So from experiment 1, I have to find the rate. And for that, I have to use the volume of hydrogen gas. Okay. What is molar gas volume? The molar gas volume is basically a 24 decimeter cube volume, which is given over here. If you don't remember, you can easily find in the constant table values here. See the molar gas volume. Normally we use it 24 decimeter cube per mole. Okay. So here it is. So it suggests us that it is 24 dm cube per mole, right? So if I use the volume from the experiment 1, which is 64 centimeter cube, and divide it by 24,000, because if you multiply this by 1,000, it would become 24,000 centimeter cube per mole. Can anybody solve me and tell me the answer? Yes.
There 2.67 exponent minus 4.
2.67 exponent minus 4. Now divide it with 60, because here that they told us that these number of moles are produced in 60 seconds. So divided by 60.
So 4.44 exponent minus 6.
4.44 exponent minus 6. That is mole per dm cube per second. So our answer over here would be 4.44 exponent minus 6. Is this clear to everyone?
Yes, sir.
Sir, DM cube कहाँ से आया?
You are talking about this over here?
Yes sir, क्योंकि वो जो शुरू में जो हमने 6.4 सेंटीमीटर क्यूब अपॉन 24,000 किया, उसमें सेंटीमीटर क्यूब्स दोनों कट जाएंगे और पर मोल जो है वो मोल ऊपर आ जाएगा. फिर हमने उसको सेकंड से डिवाइड किया तो वो मोल पर सेकंड हुआ है अभी तक.
So if you consider it for a 1 dm cube, so it remains the same, right?
ठीक है सर, सही है.
सर इसको जो आंसर है इसको 1 से हम लोग डिवाइड नहीं करेंगे.
So
Okay,
it remains 1. That's why I directly use dm cube per second.
So सॉरी, हम लोग को डीएम क्यू को नीचे लाना होगा, तो 1/4.4 into 10⁻⁶ नहीं करेंगे.
No, why? These are the moles, right? So sorry, these are the moles, and this is the second. So I got mole per second,
Right.
right? And do this. I just skipped this step. Okay. Now, the rate equation was found to be rate is equals to rate constant K concentration of H2PO2 negative and square of the concentration of hydroxide ions. Showed that the data in the table 2.1 consistent with the rate equation. Okay. So we have to prove that the concentration, the order with respect to H2PO2 is 1 and the order with respect to hydrogen peroxide is 2. Okay. So let us consider experiment 1 and 2, because in experiment 1 and 2, the concentration of hydroxide is exactly the same. And if you see the change in the concentration of H2PO2, it is exactly getting double. And if you see the change in the rate is also getting double, right? So here I can state this, that from experiment 1 and 2, as the concentration of H2PO2 doubles, the rate of reaction also doubles, hence order with respect to H2PO2 concentration is first. Is this understandable to everyone? From experiment 1 and 2? Yes, is this clear?
Yes,
sir.
Okay. Now, for example, if I compare these two, experiment 1 and experiment 3, so isn't it the rate is increased by the concentration of H2O2 is increased by 3 times, right? And if you compare these two, the concentration of hydroxide is decreased by half, right? Oh, sorry, decreased by 2. So by which factor this is actually changing? Is it changing by 3/2? Yes, can anybody confirm me?
So 3/4.
3/4. So see that
सर 3/4 नहीं 4/3 है क्योंकि अगर हम नीचे की तरफ मल्टीप्लाई करेंगे तो 6.4 मल्टीप्लाई बाय
no, it would be 3/4.
अच्छा
Check again. If you multiply 6.4 by 3/4, you are getting this.
सही है सर
Okay. And if you see, basically, I put it divide by 2. Instead, can I put it by 1/2?
Yes.
Okay. Now see, We know the order with respect to H2O2, and what is the order with respect to H2O2? Yes,
1.
one, right? First order. So I am observing that the increase is by 3 times, and due to this increase, the rate is also increased by 3 times. Here the rate is changed by half, or concentration is changed by half. Due to this, here the rate is actually changed by 1/4, which is indicating that the hydroxide ions order is second, because its concentration is decreased by half, but the rate is decreased by 1/4. Is this understandable?
Yes, sir.
So I can write over here that from experiment 1 and 3, the concentration of hydroxide ion is changed by 1/2, and the rate is changed by 1/4. Due to this, order with respect to concentration of hydroxide ion is second. If anyone have any confusion, do ask.
सर OH वाला रिपीट कर दें.
Okay. When we are figuring out the order with respect to OH, we already knew the order with respect to concentration of hydroxide ion, right?
Yes.
Okay. So if you see and compare the reaction 1 and reaction 2, reaction 1 and reaction 3, in reaction 1, its concentration is 0.40, and in reaction 3, its concentration is 1.20. I am comparing reaction 1 and reaction 2 over here again. The concentration of hydroxide is 0.20, and here it gets 0.10, right? And here the rate is 6.4, and here the rate is 4.8, right? Now, Arsh, did you agree with this, that concentration of H2PO2 negative is increased by 3 times, right?
Yes.
And the concentration of hydroxide ion is changed by 1/2,
Yes.
right? And this is actually changed by 3/4. Till here, is this clear?
Yes, sir.
Okay. Now see, if you split it in this way, for example, that 6.4 is actually changed by 3 times and then changed by 1/4 times, right?
Yes.
And we knew that the order with respect to H2PO2 negative is first, right? We are sure about this, right? Yes. Yes, Harsh.
Yes, sir.
Okay. So from this, I can surely say that this change in the concentration making only this change over here, right?
Yes, sir.
So the this change is actually caused by this one.
Yes.
So if you see, if you take the square of the 1/2, you will get 1/4.
Okay, sir. Clear.
Okay. Now state the units of the rate constant K for the reaction. Okay. To find the K, let me work over here. That rate is equals to, and if it's a rate over here, so its unit would be mole per dm cube per second. And in the denominator, I must have mole cube and dm minus 9, right? Because of one square and one simple. Or I can write it in this way, that mole per dm cube and then mole per dm cube whole square. So this would be cancelled with this one. And when I shift mole per dm cube whole square in the numerator, it would become mole inverse square dm6 and second inverse. So the unit over here would be mole inverse dm6 and second inverse. Is this clear to everyone? Yes.
Yes, sir.
सर मोल इनवर्स 2 नहीं आएगा.
Mole inverse square.
My square, my bad.
Yeah, mole inverse square. I want to write mole inverse square. Sorry. It's mole inverse square dm raised to the power 6 and second inverse. Okay. The experiment is repeated using a large excess of hydroxide ion. What does this indicate? We have discussed many questions earlier as well. Yes.
It will not be in the rate equation.
Yes, it will not be the rate equation. It now, as it's in a large excess, so it is not going to, does not affect the rate. So it would not be in a rate equation. Under these conditions, the rate equation is over here. Yeah. So in this rate equation, there is no hydroxide ions concentration. Okay. K1. Okay, it's a rate constant. No, it's a rate. Calculate the value of half-life for the reaction. Yes. So there is a one expression we have that half-life is equals to 0.693 over K. And it is, I have told you, it is for the first order only. And now the reaction becomes first order. So we would use this. Let me show you the equation. Where is reaction kinetics? See over here. See, that for rate constant from half-life, we would use this expression and this expression for the reaction, which is first order reaction. So (0.693) divided by 8.25 exponent minus 5. Yes,
8400.
84, 8400. Okay. Now, describe how an increase in temperature affect the value of rate constant K. Yes.
सर रेट कांस्टेंट की वैल्यू बढ़ जाएगी ना, क्योंकि इंक्रीज इन टेम्परेचर कॉजेज इंक्रीज इन रेट ऑफ रिएक्शन, और रेट ऑफ रिएक्शन और रेट कांस्टेंट आर डायरेक्टली प्रोपोर्शनल.
Okay. So, yes. Yes.
नहीं कुछ नहीं सर, कुछ नहीं.
Okay. The rate constant increases due to increase in temperature.
अच्छा सर, सर
Yes.
सर वो रेट की वो होती है, रेट ऑफ रिएक्शन का, रेट ऑफ रिएक्शन इज इक्वल्स टू के और कॉन्सेंट्रेशन पे. तो सर अगर हम लोग टेम्परेचर बढ़ा रहे हैं तो रेट ऑफ रिएक्शन बढ़ेगा, जिससे अगर हम लोग के को सब्जेक्ट बनाएंगे तो न्यूमरेटर बड़ा हो जाएगा ना, तो डिक्रीज नहीं होनी चाहिए वैल्यू.
Okay. Let me explain you in this way. For example, we have the concentration of H2O2, H2PO2 negative is, let's suppose, 1 mole per dm cube. Okay. Okay, Taha.
जी सर, जी सर.
And we are performing the reaction at 25 degrees Celsius. So we are going to get some value that is, for example, let's suppose it is X. That is some numerical value, right?
Yes sir.
Okay. But now I have this reactant again, but now I am again taking the same concentration. That is 1 mole per dm cube.
Yes, sir.
But now instead at 25 degrees Celsius, I would doing the reaction at 50 degrees Celsius. So what would happen to the rate?
Sir, rate of reaction बढ़ जाएगा.
By
2, factor of 2.
why rate of reaction?
क्योंकि टेम्परेचर बढ़ रहा है तो kinetic energy ज्यादा है पार्टिकल्स में.
Okay, now think, in both the cases the value of this would change. Yes.
Yes sir.
In both the cases, is the concentration of this is changed or not?
नहीं sir.
No, but the rate is going to be a greater than the previous one, right?
Yes sir.
So what it means that what would actually increase? Isn't it the K that increases? That's why I'm getting a bigger value now.
Yes sir, sir, sir.
Is this clear?
Yes sir, got it. Thank you.
So increase in temperature basically increases the rate constant, and that's why the value of the rate gets bigger at the higher temperature. Okay. A student suggests that the reaction between H2PO2 negative and OH negative might happen more quickly in the presence of a heterogeneous catalyst. Describe the mode of action of heterogeneous catalyst. We discussed this mode earlier as well. That in first case, that the reactants adsorb to the surface of catalyst then bonds of reactants gets weak new bonds are formed to produce or to form product, and then what would happen? That product dissolves and diffuse away from catalyst. Is this clear?
Yes, sir.
Okay. Now question number 3. Vanadium is a transition element in period 4 of the periodic table. Define the term transition element. I think now all of you remember the definition, and we have discussed in previous so many past papers, so I'm skipping the definition right now. Next part. Vanadium shows typical chemical properties of a transition element, including variable oxidation state. State 2 other typical chemical properties of a transition element. Yes, can anyone?
Colored compounds.
Sorry,
Colored compounds.
couldn't able to understand what you are saying.
Colored compounds and
The
acid
colored compounds.
catalyst.
Okay. Colored compounds. Beside this,
Sir, can act as catalyst.
okay, good. Act as a catalyst. Beside this, yeah, very good, Arisha. They can form a complex ions. Can be also a typical property for transition element. Explain why transition elements have a variable oxidation state. So, the D subshell and the S subshell have almost similar energies so the electron can be removed from both of them. Is this clear? Okay. VO2 positive can be reduced to V2 positive by C2O42 negative in acid conditions. Okay. In titration, 25 centimeter cube of 0.03 mole per dm cube VO2 positive is added to 10 centimeter cube of a dilute acid. A solution of 0.04 mole per dm cube C2O42 negative is then added from a burette until the endpoint is reached. The titration is repeated and the concordant results are obtained as shown in table 3.1. Showed that these results are consistent with the stoichiometry of the equation. What does this mean? That we have to prove that the moles ratio of these two would be 2:3. Okay. So what we have to prove? We have to prove this in this case that VO2 with a +1 charge and the C2O42 negative, the ratio between these two, the moles would be 2:3. Okay. So first what we would do, we take the average volume. So first find the average volume of C2O4. 28.15 plus 28.10 divided by 2. Yes, what is the answer? Yes, can anybody tell me the answer, please?
28.125.
28.125. Okay. Now from here, I can find the moles of this, which must be equal to its concentration times volume, and that volume must be in a decimeter cube, so I have to divide it with the 1000. Yes, can anybody tell me the moles of C2O4?
One 1.125 into 10 cube power minus 3.
1.125 into 10 raised to the power minus 3. Right? Now, find the moles of VO2 positive. The concentration of VO2 positive is 0.03 times 25 divided by 1000. Yes.
सर रेशियो तो आगे नहीं कर सकते हम मोल्स इसके VO2 को
Now we will take the ratio after finding the moles of both the.
ओके सर
7.5 into 10 cube power minus 4.
7.5 into 10 raised to the power minus 2. So here we got the moles of VO2 positive and we have got the moles of C2O4.
Minus 4. Sir,
Okay.
minus 4 power.
Minus 4, thank you. Okay, so if I take the ratio, see over here, if I take the ratio VO2 positive is to moles of C2O4, 2 negative, in this there is 7.5 exponent minus 4 is to 1.125 exponent minus 3. Okay, first tell me, is this clear to everybody till here? Till this step, is this clear to everyone?
Yes, sir. So just one question. The volume of dilute sulfur, would it affect the volume of the VO2?
No, it doesn't affect the volume of VO2.
All right, sir.
Okay. Now, if this would be 2, then what would be the value of x? If is equals to 3, then it is consistent. So can anybody find the value of x?
3.
Yes,
It's 3 exactly.
it's 3 exactly. 2.2 times 1.12 exponent minus 3 divided by 7.5. It's 2.125, sorry. 7.5 exponent minus 4. And you are getting the value of x is 3, right?
Yes, sir.
So we got 3. So see that we are getting that ratio 2:3, and that they have provided us the ratio 2:3. So our solution is correct. Is this clear? Yes. If anyone
Yes,
have
sir.
any doubt, do ask. Okay. I'm just going to end this question. Then we will continue tomorrow. An excess of C2O4 negative reacts with VO2 positive to form a mixture of 2 octahedral complex ions. The complex ions are stereoisomers of each other. Okay. Each complex ion contains a V2 positive cation and 3 C2O4 negative ions. Okay. Complete the diagram to show the three-dimensional structure of one of the complex ions. Include the charge of the complex ion. Okay. So see, how would we find the charge? It's V with a 2 positive charge, and there are 3 C2O4, and each one have a 2 negative charge. So the negative charge becomes -6 and the positive one is +2. So the net charge would be -4, right? Here they have shown you 2 bonds. So draw 4 more bonds because it's an octahedral, as this is a bidentate ligand, because they have shown you 2 atoms. So how can you draw? Put 1 atom over here and 1 atom over here and combine them. Put 1 atom over here and 1 atom over here, join them. Put 1 O and 1 O and join them. Enclose it in a square bracket. And put a 4 negative charge over here. Is this clear?
Yes, sir.
Okay. Now, V2 positive can be oxidized by H2O2 aqueous. Okay. Identify the vanadium species that forms when an excess of H2O2 reacts with V2 positive under standard conditions. Explain your answer reference to data in table 3.2. Okay. So yes, which vanadium species would form when we use excess of H2O2?
Vanadium oxide 2 positive.
To vanadium oxide 2 positive.
Third equation.
One minute. Okay, we are putting this in this. Its value is -2.6. So its value is smaller, so it would be going to convert into V3 positive. And then in the equation where V3 positive is further oxidizing, its value is -0.34, which is still lower. Yes, very good. So our answer would be this, that VO2 positive forms as the E naught value of H2O2.
Sir, it should be from the second equation.
Why?
1 is less than 1.77. It's gonna get oxidized further.
1 is less than 1.77. Yes. Yes, you are right, Arisha. So it would react furthest is largest. See, its value is greatest among all these. So we have started from V2 positive and it's an excess. Hydrogen peroxide is in excess. So first V2 positive oxidizes to V3 positive. And if you see in the third equation, V3 positive oxidized to VO with a 2 positive charge, as its value is smaller. So this would occur. And then it can further oxidize to VO2 with a +1 charge because its value is even more smaller. So yes, VO with a 2 positive charge would form as the E0 value of H2O2 is largest among all. Is this clear? Or largest? Then all three half equations containing okay, 1 minute, Soleha. Vanadium species. Okay. How many of you didn't understand this? Yes. How many of you didn't understand this? Okay. See, we are, according to the question, we have started from this species and this species, right? Is this clear to you, Soleha, as well? And this one is in excess. So what would happen that its value is greater or greatest or largest among all. So due to this, in the first stage, it is going to turn this V2 positive, oxidizes this V2 positive into V3 positive. Is this clear? Yes. Okay. Then if you see in the second equation, V3 positive is further oxidizable into VO2 positive. And if you look at its value, which is all even smaller than 0.77. So it means then when the V3 positive is formed, as H2O2 is in excess, so it can further oxidize V3 positive into VO with a 2 positive charge. And if you look at the next equation over here, this VO2 positive ion is further oxidizable into VO2 positive ion, and its value is even smaller than 1.77. So H2O2 is in excess when it is mixed with VO2 positive, so it can oxidize this VO2 positive till VO with a VO2 with a +1 charge. Now is this clear? Okay. Now concentrated acidified hydrogen peroxide can react with VO2 positive to form VO2 3 positive ions. VO2 3 positive ions contain vanadium combined with peroxide anion. Reduce the oxidation number of vanadium in VO2 3 positive. So see, it's a peroxide ion. Okay, let me work it out over here. That VO2, the net charge is 3 positive, and here there are 2 oxygens, and each oxygen have a -1 charge. Is this clear? So that gives me a -2 on the oxygen. So the net charge is +3, which clearly means that vanadium have a +5 charge over here. That's why I'm getting the net charge +3. So here the oxidation number of V in VO2 with a 3 positive charge is +3. Is this clear? Or +5, sorry. No, Soliha, read this. That the whole O2 have a 2- charge. Remember, whenever there is an oxide, a single oxygen have a -2 charge, but whenever in the name is written as peroxide, then that oxygen always has a -1 oxidation number. And whenever, if in the name it's written as superoxide, then remember that the oxygen over here have oxidation state of -half. So as it's a peroxide, so the oxygen, see, they have written that O2 have a -2 charge. So it means each oxygen have a -1 charge over here. Is this clear? Okay. So we have completed question number 3. Now we are going to start with question number 4 tomorrow, inshallah. Okay. Take care, everyone. Allah Hafiz.
Allah Hafiz, sir.
Allah Hafiz, Allah Hafiz, everyone.